Today we're going to talk about force, work, kinetic energy, and power. First of all, as you all know, between two masses m and n, we have a gravitational force according to Newton's law of gravity. F equal to g m over r squared. So then what is the work? Work, let's say if I have a big M here, I have a small m here, small m here. If I try to move the small m from position 1 to position 2, and the force, which is a gravity, in this case, is a force in this direction. Force is going to drag the small mass to closer to big M from position 1 to position 2. The work done by the force, usually is defined as F times S. S is the distance along the direction of force. To be more general, we can say this is a summation of F, because it's varying in different places, over ds, small kind of distance. Over each small distance, F is constant, so we can summarize all these contributions of work together to make a total. This can be written as integration. F is a force, it's a vector, dot ds, and from position 1 to position 2. If we carry out this integration in this specific case, should be 1 to 2. F in this case is g m over r squared. And what is ds? ds is the displacement along the direction of force, but that would be different from our coordinate r. R starts from 0 point, which is located right with the big m there. So in this particular case, we can integrate this as g m r from. So this should equal to g m 1 over r2 over 1 over r1. So this is the work done by the gravitational force when it moves the small m from location 1 to location 2. Okay. Now let's look at the kinetic energy of the small m. Kinetic energy, let's say E, usually is written as 1/2 mv squared. And to make this general, we can write mv is a vector of time, dot v. This is dot, okay? The two vector dot together to give you this. And if we take the derivative of this E, because E is a function of t, since the particle is moving with velocity v, which is vary in time, then you can take a derivative of this. So this derivative is a product of two vectors. You can just keep one vector unchanged and take a derivative to another, and vice versa, and add them together. When you do that, so it will equal to m dv dt dot v. Now let's look at this item here. As we all know, Newton's law of motion tells us F equal to ma, which is m dv dt. So the total force on the object moving at the acceleration a is equal to m dv dt. V is the velocity. So we can replace this as F dot V. What does this mean? This means kinetic energy changing rate is equal to F dot V, and this is defined as power, P. So basically power delivered by F to the object is equal to F dot V. Remember, F is the total net force on the object, V is the velocity of the object, and power is the power delivered to the object by this total external force. Okay. Let's look at another way. So since we can write dE dt equal to F dot V, but V is ds dt. S is the curved path that objects moving along under the influence of force. When you take derivative of that in the same coordinate, you get a velocity as a function of time. So if we look at the both sides of this and the times dt on both sides, then we'll get dE equal to F dot ds. That means the incremental energy increment is equal to the force times the incremental displacement. If we have to integrate this, then we can say total kinetic energy change should be integration of this. This kinetic energy changes equal to that. And you can write another way. If go back to previous example, if we move the mass small m from 1 to 2, you will end up with kinetic energy mv2 squared minus mv1 squared. That's the increment of kinetic energy, which is equal to this integration 1 to 2. Then we already know the result of this, Gm m 1 over r2 and 1 over r1. If I move things into the same place, then we'll say 1/2 mv2 squared minus Gm m over r2 equal to 1/2 mv1 squared minus Gm m r1. So that means you have a kinetic energy here in position 2. You have another energy we call potential energy here in position 2. When you put this together, they're independent of the position. Doesn't matter where it is under influence of gravity. We can say this equal to constant. Then you can say that's the total energy. What does it mean? This means that on the gravitational field, when objects are moving, for example, in the space, you have two stars moving around each other, you will say that the kinetic energy and plus the potential energy at any point and of the space is constant. So they're conserved, energy conservation, okay, conserved in the gravitational system. So we can call it gravitational force is a conservative force. Anyhow, we're talking about the force, we're talking about work, we're talking about kinetic energy changing rate, which is the power, and also the kinetic energy change itself, as well as the conservation of energy in gravitational field.